Alright, so welcome to this talk in a small round. We had a user group Munich. I'm quite happy to be here. I'm Dominic Benz from Innovex. And yeah, today I wanted to tell you something about what we did to make our pane smaller when building like Hadoop data warehouses. I mean, as we're such a small round, if you have any questions in between, or if you would like to see more demo code or so, just go ahead. I have some slides. I also have a demo of the whole system, so we can make it rather interactive. Just some brief words to me. I'm Dominic Benz. I'm since 4 years at Innovex. Innovex is a small IT Beratungshaus in Karlsruhe. There are like 180 people. Roughly 10% are doing big data. And we have been doing Hadoop, I think, since 2009. I started in 2011. I've been working mostly in the field of like building data hubs for companies here we were at ProSieben in Munich, we were at Otto, and basically that's where I come from. Yeah, so far, let's start with a little bit of background, what we did at Otto. So we're building at Otto a thing called the Otto Group BI data platform. So it's a fairly standard Hadoop data hub. You have some data coming in, you have data ingestion. At Otto, we're getting click streams of roughly 120 shops, also some kind of product data, which things you could buy in these shops, and all these shops, they make up roughly 10 billion euro of revenue per year. So you have this one layer where you ingest your data, where the data comes in. You have some kind of stage layer where the data is landing. That's quite typical. We have some data sources like we have like FTP data sources, we have example data sources or flat files, databases or whatever. This usually lands in some kind of staging area. Then like the core part of the Otto Group data platform is the part where we actually process the data. So we have like several shops where the data which comes in is being processed, is being cleaned, is being combined. You join the products with the logs, and you do all the linking that you want to do, and you do some kind of classification, regression, and all this stuff to actually get the valuable data out of your raw data. And the third layer is the data services layer, where you actually expose the cool data that you have done in the middle of this whole thing to the outer world. So at Otto, you have some data services like some kind of customer profiles, which you use to do some kind of targeting. We had a data service which was called search term suggestion, which well, the main goal was to find like similar search terms for searches which did not yield any kind of result. And there was one actually funny service. It was called fit prediction. This service did actually predict when you were buying clothes in a shop. It was predicting which size you needed. And I mean, if you have ever told your girlfriend, oh, I think you need one size larger, then I think you know that here in this area, then something like a false positive was really maybe very dangerous. So that's really a funny service. But that's the basic layout. With data coming in, we wrangle it and we expose it to the outer world. From a technical point of view, this whole thing here takes place in Hadoop, and basically our main unit of storing data are actually Hive tables. And like how many of you have been working with Hive already? Okay, so basically, as you all know, Hive is some kind of relational layer over the HDFS. You define some kind of schema on top of some files which are sitting in HDFS. That's like the core layer of the Hadoop data hub. In the middle, where we do the whole kind of processing, we did the whole thing using Spark jobs, using MapReduce jobs, and using Hive queries. And those jobs were being orchestrated by some kind of workflow tool. At Otto, we have been using Oozie, but you also might imagine Talent or like any tool we're just discussing in the kitchen. So, but in the middle layer, the core point is you have some kind of graph of jobs, you have some kind of dependencies, and you would like to run through those jobs and do your kind of computation. And of course, when you have many jobs, one thing that is important is you need to kind of orchestrate these jobs. You want to schedule your runs nightly, once in a week. You want to say, I want to start this job when new data comes in. So So you want to be able to schedule time-based or also data-based. And the tool that we used at Otto was Oozie for this purpose. So how many of you have been using Oozie so far? Are you familiar? Okay. Cool. Have been using any other kind of schedulers in this area, like Airflow, Pinball, Azkaban, so far? Or okay, so mainly Oozie. Okay. So that's also what we used at the beginning, and I'm shortly going to tell you what we saw as the limits of Oozie, actually. Because our main problem was that it wasn't agile enough for our case. So basically the point is that you don't have like one single layer of this whole data hub, of this whole platform, but in our case it was the case that we had like 120 shops, and for each shop we needed one table in each layer. And of course, as some data comes in daily, we need the whole thing like daily partitioned. And so it's really like a lot of layers that you have to control using Hive-PDL scripts, for example. And this is really kind of cumbersome. So one thing that really made us a lot of work was when somebody came and said, please, I want to have a new table. Then what do? You write some kind of TDL script, some Hive-TDL, you write some kind of job which fills this table, maybe a Spark job, maybe some MapReduce or another Hive query. You add this very job to your workflow. So maybe you add in your Oozie XML, you add a further section, please use this Hive query to fill this table. You integrate it into your schedule. This means you tell the job to run daily, nightly or so. And finally, you have to recompute everything that is necessary to fill this table from all your circle data. And then again, as we just saw, testing is really an issue in these kinds of things. For Oozie, we had some kind of testing approach. We were using Fitness, which is some kind of test wiki. We were calling Oozie jobs, manually inserting data into tables and checking outputs. But the whole round trip time was really slow, so we had to wait until the test was running. And when you had some kind of syntax error in your Oozie XML, you only found this very late. So the whole testing cycle was so slow, and the outcome was that nobody was writing tests, of course. I'm sure you know this. So the testing here really was a big problem. It's even worse when somebody came and said, okay, please add a new column to your table. Then you have to write some kind of TDL migration script which adds this column. Then you have to adapt the job which fills this table. You have to maybe adapt the workflow. Then you have to delete some kind of obsolete past data of this table because the past data doesn't have this column. And you have to manually prepare, or you have to manually start the jobs which actually fill this table. So this is really kind of lots of manual work. And even worse it becomes when somebody said, all right, I have some change in the logic which fills a certain table. Then you have to maybe write some kind of TDL migration script. You have to adapt the job with a new logic. You have to maybe adapt the workflow, and you have to run the whole thing for your past data. And the things you have to do here, even on top, you have to check if there is other tables which depend on this table. You have to start the jobs which fill those. And so it's really quite a lot of manual work to find out what the impact of these changes are. So you really have to do a lot of manual work. You have to reload everything. And that's something where we said, okay, we want to do it better. This was something that really took us a lot of time. And so we did something on our own. We wrote a tool called Schedoscope. And here the approach is a little bit different. The core idea, like one of the mantras of Schedoscope, is that schema is code. So we actually stopped writing Hive-TDL scripts and we started to write little Scala case classes which do represent nothing else than basically Hive tables. So basically you write a little case class which has some fields which are actually fields of a table. And so I will go in detail what this looks exactly. But then the idea is you write this kind of view. This is our like the main unit that we have in this system. Then on top of this, we really wrote a very cool testing system, because once you have the schema as code, it's really easy to generate test data because you know the schema, you can generate data quite easily, and you can test quite well which kind of data came out of the computation job. And so we built this kind of testing system. And finally, one of the core points about Schedoscope is that we have something called goal-driven scheduling. So basically what you write is you write a view and you specify which other views this view is dependent on. So basically specify which kind of input this job needs. Everything in Scala, and based on this information we can actually compute some kind of tree of dependencies from one table. And so if you tell the system, please materialize one certain view, this means fill one Hive table with data, the system can automatically determine what do I have to do before. Do I have to fill other tables before? Did the schema change? And so on. So this is like the main idea of Schedoscope, and from our experience here the whole testing times were much smaller, we were much more agile, and yeah, so basically the talk today is about telling you about this. So basically I don't want to sell anything. This tool is like open source. It's of course not perfect yet, but I think it's also not the only scheduling system in the Hadoop ecosystem, but I think it has some points which are really special, and maybe you have some kind of project where you think, all right, this might be a fit, and of course we are also happy to have people who help us to build Schedoscope further. So what are the main features of Schedoscope? As I said, the main mantra of Schedoscope is that schema is code. So we basically wrote some kind of Scala-DSL for specifying views. So a view is, in a way, something like a Hive table or a Hive table with a certain partition specification. It's like specified as a Scala case class. The class names are the table names, the package names is the database names, and the main benefit is that we can use Scala's static type checking for the whole consistency issue. So we will never do some kind of typos when like writing DDLs because it's all code. We can do really checks at compile time. We can use Scala abstractions for naming conventions. So for example, if all your tables have some kind of ID field, you can use this kind of interface, or you can mix in this thing, and then all will have the same ID field. And finally, you can use the whole power of your Scala IDE to actually specify tables. Right, so far about the tables. What about the fields? The field definitions are, as I said, basically member variables of this very class. So here we have a table which maybe holds information about a certain brand, or here we have a table which holds information about some kind of product. And you can basically specify which fields are part of this table by basically specifying member variables. We support all the primitive types of Hive. We support complex types, maps, lists, and structs. And by doing so, we can basically piggyback on the whole type safety mechanism of Scala. And also, once we have schema as code, something which is cool is that it becomes very easy to detect change, because if I add some kind of new field here, I can actually realize it, and in my whole dependency tree, I can see, all right, this DDL has changed. I have to recompute everything that depends on this. So you can do all this cool kind of dependency checking directly because it's all code. And basically, one thing that is really different from Schedoscope compared to the tools out there like Uzi, Azkaban, Airflow, Pinball is that basically Schedoscope also manages your DDLs. So you will never have to reapply some kind of Hive DDL by yourself, because when some kind of schema has changed, then what the tool does is it drops the table with the old schema and it adds one with a new schema. And that's really a core point, because the tools out there, they don't do this. There is pros and cons of this, but in a way, this is cool because it takes away work from you, but it's also something like in some organizations, people are maybe they come from the like SQL background, and if you can't show them like a real DDL script or so, they are maybe all help. I have to write some kind of Scala case class where I need a new table. So it's like a layer on top, which abstracts away the table below, but which has a lot of benefits, as you will see.
So it also makes the data migration.
Yeah.
So okay, like a Hadoop warehouse on Rails. Yeah. So because you don't define your tables directly, so just like like in Rails. Yeah.
Yeah, kind of it's like a layer on top. And if something changes, we can manage the thing below by our own. That's one core point. Right, as I said, a view is basically a Hive table with some kind of partition. The partitions are basically represented as constructor parameters of a table. So basically, if you want to instantiate a view for a certain day, you can basically instantiate this view, as you see here, with some certain parameters. We support in this DSL currently Afro, text, and paquet as in storage formats. We can have comments for documentation, and yeah, and the benefits is that you can have any kind of arbitrary loading granularity. So you can have load per shop, per day, month, year. You can store in different way, and you can basically document, or you have all the infos that you add here directly available at like runtime in the UI in the system. And the second core point, as I said, one core point of the system is that schema is code. This is the one thing. And the other thing is that when we write a view or a table, we directly specify the other views that this table actually depends on. And we do this using lambda functions. So you can, in this section here, you can say that this very table, this table product with brand, it needs at first the product table, and it needs the brand table to be able to compute itself. So here you say that this view depends on some other view with the same parameters as this view here, and here also. So, and that's the second core point of the system, that you have the dependencies like dynamically in the class where you specify the view itself. So you have one place where you actually specify everything. Like usually when you think about USI or about any kind of other workflow tool, usually you have to specify a whole dark of jobs. You have to tell, right, this job depends on that one in some kind of XML file or so. And here you can use like Scala's computational power to specify the views that this view actually depends on. So basically, you might express some very complex dependencies. So if you might have some table which basically holds information about all the things that people have bought when there was full moon or so, or like every 13th day in every second month, you could express this right here. And this is something that is more difficult when you specify the dependencies in an XML file, because you just can't do it. And that's the like second core point. In the view itself, you actually specify what you need to compute the view itself. And the last code element is that once we have the schema as code, once we have the dependencies as code, we finally also specify in the class itself the code that is needed to fill this very table. So you have like one class where you basically specify everything. You have the schema, you have the dependencies, and you have the rules or the jobs to fill this very table. So in this very example, this very view is being filled by some Hive query, which is written in some SQL field, and which is being parameterized with these values here. So basically, we support like plain MapReduce. We support HiveQL pick. You can call USI workflows from such a view. You can use not a hell script, but like a hell of a shell script. And and you can, and there are some kind of file copy operations. So this is what you can write directly in your view itself. And for exports, we use Morphline, which is a little ETL tool, or like a Java-based ETL tool coming from Cloudera, which we use to export data to Redis, CSV, or to external JDBC connections. And the main thing what this enables us is that we have some kind of goal-driven scheduling. So if I want to access this table, I just tell the system, please, I want to have you, and please materialize yourself. And then when the view computes its dependencies, sends messages to them, tells them, I need you, and then they do the whole game on their own until we are down at the leaves. Right, and we also had, as I said, because we have the schema as code, we have the whole transformations in one place, we were able to build a really concise test framework, because you can define also test cases for views. When you specify the input for testing, you have, because it's Scala, you have type safety, which is really cool, because you will never add some kind of wrong data type in the table. You will never have, again, syntax errors when you insert test data via some kind of custom SQL script, because it's all code. We have done the test framework in a way that it runs completely locally, so you can run it, so basically fetch all the jars, all the configs that we need, and you can run it on your IDE, on any operating system. You don't need a test cluster or anything. Basically, you can sit in the train and develop your jobs. And you can use the whole power of Scala test assertions to check that the results are right. So we are in a way piggybacking on Scala test to make the tests easy. And the benefits are, of course, that you actually, first of all, have tests, that you have more tests, that you have some kind of fast round trip time. So basically, from our experience, a test here runs where you fill, let's say, 1 or 2 input tables, you run the transformation, let's say a Hive query, and you check the results. This will run in total something like 20 or 30 seconds. This is like a much lower round trip time compared to when you write an USI job, have to upload the USI job, you have to start the coordinator, you have to check the output, blah, blah, blah. So we really have a small round trip time, and finally the ultimate goal is to some kind of test-driven development. And of course it's integrated in the IDE, because there's the Scala IDE where you can start tests. One more thing about the test, this is how you specify input data. So this is like a test fixture, fixture, that's also how people call it sometimes. You say, all right, I need input data from a certain table, which is called WebTrans test. And you can specify the input, for example, row by row, but you only need to specify the fields that are needed for your very test. If you don't specify a field here, which is present in the table, we fill it with some kind of random value. So we basically generate random values for like uninteresting data, and you only specify what you have to unspecify. When you write a value here, it is type checked against the type of the column. This is cool, and as I said, you never will mistype a column name again, because it's code and you will see it directly at compile time. And so this is like an example where you actually specify things row by row. But of course, as it's Scala, you also could use some kind of for loop and just generate 100 rows where one field has a certain value. So this is how we actually specify input data. Then we run the job, and here, this is like the main test class. So if the data that we just wrote is the input for a job, we say that this job is based on our input data. Here we run the job. And we say that the number of rows returned should be 1. So this is like plain Scala test, if you ever work with this. And then we can basically fetch from the result, row by row, what we want to have, and we can check the outcome. So here, like the main idea is that you're really able to unit test your transformation. So you actually specify a small controlled set of input data, you run your job against this, and then you know exactly, all right, I know what I want to get out. Of course, this is just one aspect. It's also important to run it on like bigger data to see the whole cluster thing, but you can do unit tests with this. That's the main message. And so one point about the goal level scheduling, as I said, basically you don't run workflows when you work with Schedoscope. You only tell Schedoscope what you want to materialize. So the main command is, please materialize a certain view. Then this view gets the message, please materialize yourself. The view knows its own dependencies. It sends to them, please materialize yourself. It goes down to the leaves. And finally, the point is that the system basically determines on its own what it has compute and what not. So like this whole manual process, which we had before, is just gone. So basically the system, so when you tell the system, I want to have this very data, it knows by itself what it has to compute. And that's like the basic idea. And this way, we don't make any distinction between loading and reloading. The system can also detect, as I said, when some schema has changed. It knows what it has to recompute. And yeah, that's the kind of the point of the goal-driven scheduling, which is also something that is really special among the less scheduling tools that at least I know. So if you have Uzi or Azkaban or how they are called, they all work in a way that you have some workflow or some kind of sequence and specification, and you run this sequence, but you don't have this thing that you can tell the system, I want to have this data, and the system knows itself what it needs to compute everything. All right, some brief words about the scheduling architecture. So basically, when you write or when you set up your Hadoop Data Hub with Schedoscope, you write some kind of project-specific view code. Here you basically write your tables that I've just shown you. You have the framework itself, and you bundle this to some kind of project-specific Schedoscope web service. So this is basically the heart of the whole thing. When you want to materialize a table, you always talk to this web service. It has some REST API. It has a CLI or a model interface. It has what the tools have today for like talking to them. And then this web service basically sends jobs to the name server for file system transformations, to the Hive server for Hive jobs, to the Uzi server for Uzi jobs, and to MapReduce split transformations. It talks directly to the resource manager. And as I said, the core source of schema is still the Hive meta store. So as I said, we have like one layer on top by using code for the schema. And underneath, we materialize the schema again in the Hive meta store because it's our main source of truth for holding information about the state of views. So in the Hive meta store, we're actually having like pointers or little checksums. If a view has been computed, when it has been computed, with which version of its transformation it has been computed, and which version its DDL is from. So basically, we use the Hive meta store to store many checksums, and by having all those checksums, we can really find out what we have to compute. That's the point. So here's a little example how this materializing chain works. So if we have some small kind of view dependency graph, we have one table which is the brand inventory, which depends on a table which shows products and brands, which depends on two tables, product and brand. Then let's tell this table, or please materialize yourself. Then what happens is, because the tool can find out what it needs to compute itself, it puts the state of the target table in waiting. It sends a materialized message to its dependency, and then this dependency does the whole game again. So it knows what it needs to compute itself, then it sends a materialized message to the leaf nodes, and once you're down to the leaf nodes, you can't go further, then they will start to run, they will perform their own transformation, and once they are done, they will send back messages to the guy who asked them, actually, and then this guy knows, all right, my two dependencies are met, I can actually compute myself, and then we go up the chain again. And this is basically how Schedoscope does determine the things that it has to compute. And this is something, as I said, that the other tools don't do, at least in this way. So what happens if we have a new date? So let's say this table is like monthly parameterized, and on the next day there is new data coming in. Then again on the next day we tell this table to materialize. Then what happens is, again we send down the materialized messages down the road. We tell our dependencies to materialize, it goes down to the leaves, but then, because these have been already materialized yesterday and they didn't change, we don't do it again. So we can actually realize that we don't need to do it again, we have to waste computational resources, but we have to recompute it on the lower branch. We start the computation, the messages are propagated up again, and finally we run this one again, because one of our dependencies has changed, created like a new dependency. So what happens if we have a change in some kind of transformation logic? So let's say the query that fills this table has some other join condition or so. Then it would go like this. If I tell our main table to materialize, again I send the message here, then it's being sent down the road, down to the leaves, it goes up again, and when we get back here, because the tool compares the checksum in the meta store to its current checksum, it knows that the query which fills the table has changed, and it knows that it has to run the query again because the data will be a bit different. And then once this is done, we have to recompute the main table, of course, because the input data has changed. And one pretty similar use case is when the DL of the view has changed. So let's say here we have some kind of new field in this view. Then again, if you tell, let's say here we have some new table. Again, we send the materialize command to our table of interest. So this is our goal. This is our goal-driven scheduling. Again, we send the messages down the road. We go up again, and when we go up, we know that we have to fill the table again because the schema has changed. This is what we do with our checksums in the Hive data store. And again, we go up, and finally we have this table with the data from the new schema of its dependencies, and that's what I meant by you basically have you have much less manual work to determine what you have to compute, because the system knows so much about its views, about its dependencies, about its transformations, and about the whole structure. Right, that's kind of the core point. So the current status is that basically the tool is used in production at the Otto Group. They're running basically the whole data hub based on this tool. The whole cluster utilization has become much better because so for example, USI does this. When you have a USI workflow which triggers Hive workflows, then the starting of this workflow is again one further produce job. So we have in your cluster many small produce jobs which do nothing else than starting other jobs. So this was something that we actually realized with many small jobs that the cluster was full, but the actual working jobs which are filling the tables, they got less resources, and this is something that we don't have here. So the whole process is much more streamlined and much more optimized. As I said, we have a test framework, we have a scheduler, it's documented, there's a tutorial that you can download and run. We currently support file system transformations, this means copy operations from to HDFS. We support MapReduce, Hive, Pig, USI workflow, and small files and shell transformations. We are currently working on migrating to Scala 2.11, and we plan to integrate natively Spark and Flink transformations. It's of course cool because it's a really natural match with Scala for writing views, with Scala for writing Spark jobs. Looks like a perfect match. And we are working on what we call replacement. and finally on a nice web front end as well. And finally, a little comparison with the other tools out there. So as a disclaimer, I've been working really a lot with Uzi at Otto, so we were pushing Uzi to its limits. I've been working a lot with Airflow, and of course in Schedoscope there is Azkaban, which is also a very old system, and there is Luigi. And if you compare them, basically the things that actually distinguish Schedoscope from them is that basically it takes care of the whole schema management. So you don't need to write anything else, for sure. It takes care of the whole change management of your jobs, basically. There is a test framework, and it's basically goal-driven. And that's something which actually distinguishes Schedoscope right from the other tools.
But when you talk about goal-driven, it still means like you want to have the goal to be provided at a certain date and time, right?
True.
So it's still date and time, but more than just date and time.
True. I mean, so basically what we had at Otto, that's a good point. So we had basically a daily job, which did nothing else than polling the REST API of Schedoscope to materialize this certain view on this very day. But the point is that you only have to specify the goal, and all the rest is done by the system. That's the point. Yeah, so far about the main contents of the talk itself. As I said, Schedoscope is open source. Basically, it's for free. There's some kind of tutorial that runs on some standard Cloudera virtual machine, which you can try yourself. We are on Twitter. There's a Google group. And if you have any kind of questions, we're also always happy to hear about people who do stuff with the tool. Currently, we are mainly 3 to 4 people, which kind of drive the tool, and that's basically the point. I also have like a little demo of what the interface looks like if you want to see. Okay. So really what you see here is just, you can't see it here. You have to see first of all, because right now Eclipse is still open, so that's very small, but that's an example of a test. So this is not a demo, this is just to see. So here we have a test. Here we specify input data for the test, and the point is that once you make a wrong type here, if we say I set the job type to 1, then you get an error because it knows that job type needs a string. So basically you have type safety when writing your test. And so here we have basically a standard Cloudera demo for M. It's 5.4. I've basically checked out here in this directory. I've checked out our tutorial, and in the tutorial, we're basically having some demo tables. They are based on like OpenStreetMap data, and if you want to run the demo, you have to this way. You have to start the system. It may take a while because I think I'm not online here. It won't download the thing. But then what the demo does is it will actually instantiate the CLI, and using a CLI you can basically send the commands to all the views which are defined in the demo project. Right, it's timed out finally, it's good. take some seconds. So here we have the CLI. What it does at the beginning is it talks to the meta store, it fetches all the information from the tables that it knows, but currently nothing is materialized. So the first thing that you do is, let's say we want to materialize a certain view, then you do it like this, you just tell the system to materialize a certain view. This is the database, that's the view, and this is what you tell the system. Then the system sends the materialize command to the view, it computes the whole dependencies, and then you can, using the views command, you can basically see all the views and their status. So basically, you can see that some are in the state waiting, some are already materialized, and some are already transforming. If you want to see which views are currently transforming, you can show the currently running transformations. Currently there is 2 Hive transformations running. What they do is they talk to the Hive server, they send the Hive TDL or the Hive TML to the server, and if you have a look at your resource manager, then those 2 jobs will show up, and this is like the basic way how the views are being computed, and as the thing will go on. This is just a little demo for him. It always takes quite a long time to run the thing on such as a single machine. Here you can basically inspect how the views are being computed and how the state of the views is changing. Right now there's changing not so much because we have this many Hive transformations running in the demo. And it just takes some time on this little VM, but this is like the basic idea. And as I said, you can always see the running transformations here. That's like your main interface, and that's what you the things that you can do here in the interface can also be done via some kind of REST API. So this is how you talk to the system. Yeah, so far from my part. If you'd like to know, first of all, thank you for your attention. If you have any more questions or anything more you would like to see, it's all around. There is, I think, 2 pizzas for each of you now.
How long did it take to build this? Well, how long are you working on this?
Yeah, that's what I said before. It was really astonishing for me that Otto did this with us, because it really had some free time. So we were basically 3 people, and roughly altogether, I think I would say at least half a year or so. So we're starting with some early version, as always, and then we're seeing, okay, it works quite well, but in total it's at least half a year or like 9 months for 3 people. So Otto made quite a large investment. I think it pays off because anything they do from now on will take them so much less time that it will hopefully pay off, but it was a large investment from Otto and also from our experience. We are doing 2 projects like since some years. Like this kind of freedom to build on something like this is something that you don't find often. But I think it's a very typical way how tools are emerging in the big data field, because like most of the tools, they come from the industry because the industry has some problem that none of the tools out there is solving, and the big companies like Google, Pinterest, Airbnb, they have the manpower to build what they need, and then they open source it. And basically that's the same way how this tool basically emerged. We saw, right, the like current scheduling stuff out there isn't good enough. We have to do it on our own, and we had the money, the time, and the people with the knowledge to build it. But it's not a problem.
That's why I'm asking, because well, I'm not using Hive that much, but I'm using Hawk. That's some special tool from Pivotal, based on PostgreSQL. It's quite cool if you do selects and joins and everything like that. But we are also thinking about building some system on top of that, because it's just absolutely incredible, painful to somehow manage your data dependencies on a shell script base, because the system does not provide something else or something other, and just you could maybe just write shell scripts and put it on cron. And you need to build everything like this, like you said, on a daily base, add some partition, fill in data and all that stuff. And from that point of view, it really sounds like the same thing we are thinking about to somehow build. I think everyone who uses an SQL or Hadoop thing now needs to build something like that, because if you have big systems with big tables and need to have partitions and batch loading, micro batches and stuff like that, it's always going to end up in something like that.
Yeah, true.
Yeah, I've never seen this goal driven is amazing, because in a classical BI environment, you're ending up with you're working with when you're working with Cognos, as an example, you have a lot of single small cube files, and everything's depending on some way. And most projects or companies who are running this, there's one guy deep down in the cellar who knows how everything is connected together. If this guy is ill, sick, or dies, nobody can say much about the system. And here it is inside the definitions, which is far beyond ETL tools I have seen so far. So.
And the Go thing is a really interesting point, because lots of other tools, they are also using the DAG, the graphs, for just building their dependencies, like Spark does or Pig does.
So many.
That's just the way you should do it, but the SQL on Hadoop engines, they don't. I've not seen one.
Exactly.
That's really a gap that inside. Or outside there in the open source world, that no one has solved it yet.
Even as a professional, when you're going to license software, so.
But did you already try to implement? So it's really based on Hive. For storage, everything you use is like Hive, and not just flat tables or files in HDFS.
So currently, the Hive Metastore basically holds all the metadata about the views. That's the point.
But you also use Hive tables for storage of the data, right?
Yeah, exactly.
So not files in HDFS, but always files based on Hive tables, or coming from Hive tables.
How many other way around? You have Hive tables on top of existing.
But you could replace this I assume the Hive with any SQL or storage engine.
Would mean like you have to do some work on that.
But right now, the whole
of course. You can play them.
As far as I understood, you really have fun on this job implementing it for analysis.
Sure. Rani is also fun.
So okay, how does this scaling of this partitions working? So
pardon, how does it?
When you're running partitions,
and so basically, when I showed you that you materialize, so this very table that I tell the system to materialize, it's not being parameterized. There is no kind of partition keys. It's just a non-partition table. If you would have some partitions, it would tell the system to actually would need to tell them the values of the partitions that you want to materialize. So if this table would be partitioned, then you would just add the partition values behind. So just this was not really. So example here, that's the like main syntax of the view. So here, in this very example,
okay, so you would write a wrapper around when you have some schema for your partitions.
So all partitions have the same schema because they have the same underlying table, right?
Yeah.
So basically, this is the database here. This is the table, and those are the values of the partitions. In this case, it's year, month, day, but we just state the values here. So if you want to materialize one certain partition of a table, you would write that you materialize would tell it to materialize -v, and then you would do it like this. So in this way you would tell the system to materialize one certain partition. That's how you would basically do it. And if you have one table, for example you have one monthly table, and you want to materialize this table based on, let's say, 31 prior tables which are daily parameterized, then you would specify these dependencies in the view itself, and you would tell, all right, this monthly partitions view depends on the 30 daily partitions of the tables before.
Okay, so what about don't specify the partition date time? The partition date it just figures out that which date partition it should build.
Yeah. So that's the point. So if you tell the system to materialize, let's say, a monthly partition table for a certain month, then based on the month that you specified, it can compute the other daily partitions which you need to compute this table.
Okay, so also if I omit the months, yeah,
Mm-hmm.
and then we get a new. So we have May is finished. We're going to June, yeah,
Mm-hmm.
and then Schedoscope realizes, well, we have new months,
Okay.
and then I make a partition for June.
Okay.
Yeah, is that the case?
No.
No.
You always have to tell the goal. So if there is, let's say, June coming,
Yeah.
you have to tell the system, please materialize June.
Okay, that's what I meant with the wrapper function. So I would write a wrapper around this to because it's automatically, because I know that it says.
It's true.
Yeah.
I mean our kind of wrapper, as I said, was already a cron job, which runs every month and calls the REST API to materialize. That's our way to wrap it. But
yeah, which is the same, like whatever. Yeah. So.
Yeah. But there's nothing. So if you don't tell the system to materialize anything, it will do nothing.
Yeah, sure. Okay.
That's the point.
Yeah.
So it's built right.
But I mean, it would be able to figure out if you say I have partition based on year, month, day, yeah, and when you get it in your system date, you say, well, materialize this this view. It says, well, okay, this view is partitioned by day. Yeah? We have a new day, so I make it materialize for the new day without anything else. So actually, you would need any additional.
Yeah, true. But you would need some kind of thing running in the background, which actually has realized that there is a new day and which triggers something.
Yeah.
But if it's built into Schedoscope or if it's triggered from outside, but that's the way how you would do it actually.
Yeah.
So right now, we trigger it from outside. That's how we did it at Otto.
Yeah.
But maybe it's also a point that you have some kind of, you might add some kind of like cron expression directly within Schedoscope that does some kind of checks within the system is also possible.
Are there already other customers except Otto using it? Or people interested in using it? Because as far as I understand, it's in a quite early time for the system.
Yeah, true. I mean, it's early time. We had a system demo at this year's Strata in New York. So actually we had some kind of broader audience. The main driver behind the product is Westermann from Otto. He was talking to Cloudera and to Hortonworks, and they actually found it cool. But of course, I mean, I actually couldn't tell you like some other large installation. Like in our projects with Innovex, we have some projects where we think about using it, but so like in like one other project, we didn't use it because it's also, I think like with all the tools, this is not the silver bullet for like scheduling. First of all, when you need a new table, you have to write a Scala class, which is actually cool. But if you tell some people with BI background you have to code Scala, that might be some kind of showstopper. So this is, I mean, there's always pros and cons. But in some, let's say, technical company where you start from the very beginning, I would really suggest to abuse it. It's maybe also a bit harder when you come into some environment where the people already have a lot of stuff, where they have already a lot of big jobs steered by Uzi to do the whole migration thing is quite some work. But when you start from scratch and you want to really be fast and you're not afraid of Scala, then I would actually tell our customers to use it. But and to answer it, there is no big other customers, because as with most projects, it's quite young. You can do cool things with it, but you need some kind of will to try it out. But at least at Otto, they're really doing their daily production load. But I mean, of course, they are the ones who built it, so it's not really.
How do they manage system load? Because that's one thing I did not see up to now in the presentation or in the slides, that building a table might take a lot of system load for some time, and you have a multi-tenant system maybe running, and if you just kill it by materializing one view, how do you handle that? Just using queues and yarn, or?
Basically, that's actually Yarn's job. So basically, we talk to Hive server, we talk to the resource manager, and we use the resources that we get from this one. And if you want to share resources, maybe the Hive server would get some kind of other queue. So basically, that's not our main point, but that's not our main focus. So the whole resource management on the cluster, that's by Yarn. What you can control in our system is, so basically, like the whole steering and the coordination of like Schedoscope itself is implemented in Akka. And what you can basically control is that, let me show you this, when you just say transformations. And basically you see all the worker jobs within the system. And here you say that you have, I think altogether you have 10 pick workers, you have 5 reduce workers, you have, I think, 10 Hive workers or so. And for each transformation type, you can specify how many parallel workers you have, because in this way you can, in a way, control how you, for example, use the Hive server. If you have 200 Hive workers and they all send Hive queries to one single Hive server, then that might be a bit hard. But this is one screw that you can use. But the whole suspension on the cluster, that's of course Yarn's job.
Okay, because in systems with lots of data, it's always a problem that you run into some point that you might have a table that might have a query, because it's depending on some other table and it will run for almost ever.
Yeah.
And you have to still figure out if there is something going wrong in your system. Because of course you can test it if you type saved it before, right? And everything like that, but testing on system load is still, you will not get rid of that.
Sure, but it's something else. It's, I think, two like aspects of testing which are in a way different. So the idea is test, but you also have like auto some kind of staging area where we run the whole chain, and but and finally, in my eyes, the really final testing is always done in the prod, because it doesn't make sense to buy 2 big data systems which are both capable of handling prod, only to be able to load test it. So
yeah, I'm telling that to my operations every day, but they won't believe me.
Yeah. So, in my eyes, at least a bit of testing in big data is always done in prod, because basically only the prod system should be big enough to handle the prod data, and only there you will see the effects that you have so many jobs that, I don't know, the resource manager starts swapping or whatever. That's true.
And what was the turning point that made you realize that you needed this product? I don't know, when you hit the threshold of 100 shops, or when did you realize it? When did you decide?
And so basically, we started with Uzi, as I said, and at that time we had 60 shops which were daily partitioned through all the layers, and so we ended up to have, in summary, I think when I left the project, we had something like 3,000 Hive tables, like Hive DDLs with all the change scripts, and even rolling out all these scripts, just only rolling out the tables took 1 or 2 hours or so. Mm-hmm. And then we saw that, all right, managing this whole schema thing is just tedious. And then one thing which also was the main reason that for us was like when the logic to fill a table changed. So for example, only when you join your tables, you only join on some different field. When you had such a change, you made this change to one Hive query, and you had to do lots of other things, namely take this query, put it into a Uzi XML workflow, test the whole thing manually, and there was so much basically stupid work besides the one intelligent work to basically fix the logic, that we finally realized it would be cool to have some better way where you only do the interesting work, namely fixing the logic, and the rest does the system. That's the main point. Because I mean, really, I really don't like Uzi too much anymore. I mean, Uzi is like de facto standard for workflows. If you ask people, like many people use it, but like writing down those large XML files is so error prone. Then the testing cycles, they are so large, and you make one kind of typo with a field name, and you only like realize it 10 minutes after, and that's really a bad thing about Uzi. Yeah. So far,
Thank you.
Thank you.